Hello, my name is Hao Fang, a PhD student at Leibniz University of Hanover. My research mainly focuses on using knowledge graph and causal inference to support decision-making in different domains. We prepare a short video to present our recent work, hybrid AI approach for counterfactual prediction our knowledge graph for personal healthcare. We begin with a motivating example, then present our solution and a case study, and finally conclude with our findings and future directions. Hope you enjoy it.
Consider a person, Eva, who visits a hospital and is diagnosed with ALK-positive lung cancer. The hospital collects some information of Eva, such as age, gender, and smoking habits, etc. Shocked by her diagnosis, Eva struggles to understand why she tested positive for ALK and which factor causes this result. She wonders what her biomarker results would be if she hadn't smoked. This scenario exemplifies the counterfactual prediction, where each patient like Eva is considered as a unit. The smoking habits and biomarker results represent the treatment and outcome, and other properties are the context of the patient. The outcome under actual treatment is the factual outcome. The one under a hypothetical treatment is the counterfactual outcome. Our objective is to develop a causal model that predicts the counterfactual outcomes, helping patients understand the why behind their medical results. A major challenge in building such a causal model is the absence of a causal graph that encodes all causal relationships between properties. With the advancement of large language models, LLMs, which have been trained on millions of medical research papers, we may use these LLMs to infer causal relationships. However, LLMs need detailed property descriptions, some metadata like human understandable meanings, domains, and ranges, etc., to effectively query causal relationships. Knowledge graphs integrate this critical data and metadata, offering a structured context for querying causal relationships. With these ideas, we propose healthcare AI that combines symbolic reasoning, data and metadata-driven causal discovery, and counterfactual reasoning to predict outcomes under hypothetical scenarios. We evaluate healthcare AI using synthetic datasets generated using an expert-designed causal graph and a corresponding causal model trained from a real lung cancer dataset, comparing healthcare AI against other methods for causal discovery and counterfactual prediction. We use the Jaccard index and Pearson correlation coefficient as metrics. The results on causal discovery show that data-driven methods, PC, FCI, GES, generally underperform the metadata-driven method, LLM. Combining both approaches, healthcare AI achieves the best performance in causal discovery. These results suggest that the data-driven and metadata-driven methods can complement each other. The results on counterfactual prediction show that the causal model with data-driven methods perform better on small data sets. In contrast, the causal model with healthcare AI and expert performs better on large data sets. The LLM performs the worst on all data sets. This may be explained by the fact that data-driven methods tend to learn a simple causal model which can be well-trained under a small data set. And the metadata-driven methods cannot achieve good performance without respecting the data distribution. To conclude, we proposed healthcare AI, a hybrid method that achieves the best performance in causal discovery and competitive performance on counterfactual prediction. In the future, we plan to explore various prompt engineering techniques and apply our methods to real medical data sets.